session of this conference. We do have, I think, 5 speakers for this session. One got added from last one. And this session will be chaired by Dr. Suresh and Dr. Zakwan. And for all the presentation, you can find out at the chat section, there is a Q&A tab under which you can post your questions, or alternatively, you can raise your hands so that I can give you the speaker access and you can come live and ask questions to the respective speakers. During the presentations, I request all others to switch off their camera and mic except the speaker who will be sharing the screen. And each tile at the right hand side corner, you will be finding 4 arrows outwards. If you click that one, it will maximize your screen. Thank you. I'm handing over the session to the session chairs. Suresh, can you come switch on your camera and mic and come? Yes, I think Zakwan is also there. He can also switch on his camera and mic if he wants.
Hi, Zakwan.
Hi, Suraj. How are you?
Fine, thank you. So I'll do the first 2 papers. You can do the next 2 papers. Is that okay with you, Zakwan?
Yeah, that's fine. Yeah.
Yeah, there is just addition. There is a 5th paper from which one? From 14.5 to 14.25. Sorry, 16.5 to 16.25. That will be by Xingyao Wu, who was because of some technical difficulties couldn't present yesterday. He is also present in here. So instead of 4, we have 5 presentations for this session.
Okay, that's fine. So we can start now because it's already 2:45.
Yes.
So we can start with Manpreet. So Manpreet's presentation on the review of robotic system for aircraft inspection. Manpreet, are you here?
Yeah, can you hear me?
Yeah, we can hear you. So you can start now. I think it's altogether 20 minutes. So if you do a presentation for 15 and 5 minutes for an answer, that'd be great. Okay, you can. Yeah. I mean, you can start.
Okay, I'm just gonna share my screen. Sorry, just give me 1 second. Okay. Can you see my screen? Hello?
Yeah.
Are you able to see my screen?
Sorry?
Can you hear my screen?
Yeah, we can see your screen and we can hear you as well. You can start.
Okay. Good afternoon, everyone. My name is Manpreet, and I will be giving an overview of my paper, which is on the review of robotic systems for aircraft inspection. To start off with, aircraft maintenance is a key aspect when it comes to continuing airworthiness, and it's mainly based around finding any defects around the aircraft. So, for example, there is a microbiological corrosion which occurs within fuel tanks, impact defects on the fuselage itself from lightning strikes, for example, and also there could be any sort of structural damage around the aircraft itself. So in order to find these defects, inspection is involved. So you can have your simple basic inspection, which involves moving around the aircraft, walking around the aircraft, and conducting any inspection with the use of, for example, a magnifying glass, or any use of remote visual inspection devices, such as boroscopes, or there's the use of NDT methods. So you can, with the application of ultrasonic sensors, eddy current testing. So you have different types of checks. You have your simple checks, and then you have your more in-depth maintenance, which involves the C&D checks. So my project is based around fuel tanks themselves of aircraft, and how robotics could be applied to assist with fuel tank inspection. So as you know, fuel tanks are very challenging environments because of the presence of jet fuel, which gives off toxic vapor. You also have the lack of oxygen within such confined spaces. So the structure of the aircraft include where you have your ribs, your spars, you have your stringers, the overall wing skin, and also there are many subsystems within the tank itself, such as your hydraulic piping, fuel piping, or any sort of electronic wiring. The majority of the fuel tanks are known as wet wing fuel tanks because the fuel is stored directly into the structure itself. So the problem definition around this area is that when it comes to fuel tank inspection, it's a very time-consuming process and it requires a high level of precision. You need trained engineers, and also it requires the dismantling of surrounding structures and sub-assemblies, which is also involves additional time. And within the structure itself, you have fuel transfer holes, which are roughly around only 70 millimeters in diameter, and it can be quite difficult to conduct inspection in these confined spaces. So last but not least, there's also the exposure of all these vapors that are toxic to human personnel themselves, and this requires a lot of safety precautions. So there's four key areas when it comes to fuel tank inspection. So you have to consider all the chemical and physical hazards, and also this involves the preparation of entry and the conditions that need to be monitored while within a fuel tank itself, and there should also be emergency response plan in place. So to start off with my research, I looked into the different types of robotic systems that are currently available within the aviation industry, and there are quite a few. Some of them are already being tested, or some are in development. So looking into EasyJet, for example, they have been developing drones which can fly around the aircraft to conduct inspection of any sort of impact damages on the fuselage itself. But there are many limitations when it comes to this, when it comes to detecting defects on curved surfaces, for example. So then there are also robotic systems that have been developed that are able to crawl around the aircraft fuselage itself. So one from many years ago was one robotic system developed by Lufthansa, which was able to surface crack detection. And some of the limitations with this robotic system was and how the limitations of maneuverability across the curvature of the fuselage itself. As you know, Cranfield has been developing the Vortex robot, which has kind of overcome these limitations due to size and movement across curved surfaces. There are other robotic systems where you have your mobile robot systems that have been developed to which incorporate 3D technology to measure any sort of crack propagation. I would focus most on the two examples at the bottom because they have been working on developing robotic systems for internal inspection areas within an aircraft. So OC Robotics have been working on continuum robotic systems where the electronic aspect of the robot is placed on the outside of the hazardous environment. And there's a snake arm robot which kind of feeds into any sort of small space to conduct inspection. And this obviously you have to take into consideration your lower explosion limits and your flashpoint limits. And Rolls-Royce have been doing the same, where they have been working on developing snake arm robots that are able to conduct inspection within a engine environment, but taking into consideration the high levels of temperature. So once I had completed this area, I looked more into the oil and gas industry and nuclear decommissioning, who have been developing robotic systems over the past few many years. And I think they are personally much more advanced when it comes to the application of robotic systems in hazardous confined environments. So I'm just giving some examples. So one of them was the petroleum project, where they had developed a robotic system that was able to be fully submerged in fuel itself, and they wanted to eliminate the process of ventilation of oil tanks and the cleaning process, so much more time is spent on inspection. The similar approach is applied to pipeline robotic systems as well. One of the most trending topics right now is the use of soft robots, especially in nuclear decommissioning, where they have developed a flexible snake type of robot with the use of soft materials that is able to maneuver itself within confined space, hazardous spaces, and because it's pneumatically powered, there's no risk of explosion, for example, because there isn't any sort of electrical components present because of the soft material. And there have been other examples where robotic systems have been combined together, both rigid and soft, and that are dependent on each other when it comes to conducting inspections. So I represented these findings into two tables. So I highlighted this in the first table. You can see there's quite a big gap when it comes to the application of robotics in a confined hazardous space in comparison to the oil, gas, and nuclear industry, where this issue has been overcome to some extent. So I separated my research into 4 key areas, which is hazardous environment, confined environment, the materials that would be required when developing a robotic system for a hazardous environment, and the type of inspection methods that you could implement into the robotic system. So either just a visual camera or the use of NDT equipment. With these 4 areas, I broke them down into in relation to a fuel tank environment aspect. So taking into consideration the parameters of jet fuel, which obviously gives off toxic vapor and is prone to explosion. So the different types of limits you have. So you have your low explosion limit or your flashpoint limit. So how could the electronic side be designed according to this? So there's no sort of risk of explosion, for example. And when focusing on confined space, looking into the physical constraints of the fuel tank. So how do you design the mobility of a robot to maneuver in a fuel tank itself? And what types of inspection equipment could you add onto the robot so it's quite small in size? It can maneuver in a confined space and conduct any sort of inspection. And the types of materials. Materials separates into 2 areas. One would be the materials of the robotic system, and the second area would be the materials of the fuel tank, for example. So if it's a composite wing fuel tank, what types of defects would you be looking at? So corrosion is probably more resistant when it comes to composite fuel tanks. So there may be other impact damages that may need to be detected. So I focus more on the mobility of the robotic system and the design on the mobility side, and I'm trying to incorporate have a mobile system present which is able to carry an inspection device to conduct inspection in a small space. So my project is based more around fighter jet aircraft. So as you know, the wings on fighter jets are very narrow structures. So this is just an example of a CAD model I had made. So I have implemented the use of a tracked system, but more into the design of a snake type of robot with a modulation system in the middle. So it's able to be flexible enough, but with the use of the track system, it's more robust. So it's able to go over the different types of ridges within a fuel tank, and also if there's fuel residue present, the tracks are able to withstand this rather than having a wheeled robot, for example. So this is just one example. I'm refining my CAD models more into the type of inspection device I would want. So I've just shown an example of the robotic arm. I'm changing this because I need to have it fit within the constraints of around 70 millimeters in diameter. So the robot system itself has to be very small. So how would I design it to kind of fit around this measurement? So when it comes to the robotic side, I broke it down into two areas. One is the internal inspection. So what kind of what type of inspection method would I use? So I'm primarily focusing on just visual inspection. I think NDT could be incorporated later on for further work, for example. I need to take into consideration the lighting because of the lack of visibility within such a confined space. And the second area is the robotic system itself. So the types of mechanical components that would be required, sensors. So definitely have, for example, a gas detection sensor because you need to monitor the levels of gases in the fuel tank while it's in there. And another thing to look into is the failure of the robotic system if it did fail. You wouldn't want a complete autonomous mobile robot in aircraft fuel tank, and if it's failed, how would you retrieve it back, and what are the risks? If the robot system was very small and it failed, and how would you retrieve it back? So you could simply just apply a tether to kind of overcome this issue. So I just want to kind of finish off with the advantages of robotic application within a fuel tank. So obviously the exposure to the person who's conducting inspection of hazardous fumes is dangerous if it's not done properly. It's a very time-consuming process as well. So maybe if we did imply a robotic system to such an environment, maybe the parameters such as the lower explosion limit and the flash point limit could somehow be adjusted. So there might not have to be set to a certain extent to when a human person enters the fuel tank. So maybe ventilation, for example, which is definitely important, but maybe some parameters could be adjusted then around the mobile system, the robotic system. The other benefits would be that the disassembly of structures would not be required. So you just simply have this robot system that could maneuver in these spaces and conduct inspection. And flexibility in design. I mean, there's so many things you could do with a robotic system. You can add different types of sensors, make it much more advanced, have autonomous robot system in place. And overall, it would reduce the downtime when it comes to maintenance. So it could be cost effective if it's implemented in the right way. So this is just the overall summary. So my project is obviously focusing on the aircraft fuel tank inspection and how could this be applied to, how could a robotic system be applied to fuel tank, all the precautions you have to take and all the parameters you have to consider, and how would we be able to successfully achieve this. So the one thing I would say is this project is quite a large area, so there's many different things you can look into. So I'm focusing more on the confined space and the mobility side of the robotic system. And that's it. Thank you very much. Any questions?
Is there any questions from the audience? Okay, in that case, I'll ask a few questions. So in terms of getting access to the fuel tank, how many access points do you normally have? Like, is there a number of access points, or is it just one access point where this robot has to go in?
So because I'm looking at the Typhoon fighter jet fuel tank, so the access point is, so I'm looking at the port side of the wing, to the left side, and that's from above, so the top panel of the wing. So it would somehow have to be dropped into the fuel tank. Oh. So there's one entry point that's been stated.
Oh, okay, just one entry point. And how easy it is to like the snake-like robot? How easy it is to do the human interface to the snake-like robot? Like, is that quite easy to maneuver it, or is it difficult to maneuver it in a full tank context?
So I haven't looked into implementing the interface side to this. I mean, the only area that I have, well, because it's the basis of the robot, I would want it to be remote controlled. So where the engineer could somehow control the robot system from like a handheld device. That's the most I have thought about this so far. It's an area that I haven't really looked into. I think I've just focused very much on to how do I design this system.
Okay, all right, thank you.
Thank you.
Okay, in that case, thank you, Manpreet. That was a really good presentation. And we move on to the next speaker.
Okay, thank you.
So next speaker is Abdullah. He's going to talk about the emerging challenges of digital aircraft operation and maintenance, a knowledge-based perspective. Abdullah, are you around? Abdullah? Arjit, is Abdullah around?
Figure it out because his name is there in the participant list. I'm just trying to search for him on the tables. Just 1 minute.
Okay.
I dropped him a message in case he's somewhere else and can join, because when the session was starting, I could see him on table 3.
Okay. So in that case, like we move to the next.
Yeah. Yes, that's better, I think.
Yeah. Okay. So the next one is on about. So this is at 325. It's about aircraft predictive maintenance modeling using hybrid imbalance learning approach from Maren. So Maren, are you around?
Yes, I'm here. Can you hear me?
Yeah, I could hear you. How are you?
I'm doing fine. Okay.
Okay, so are you okay to present yours now because Abdullah is not around?
Yeah, that's fine. I'm going to carry on.
Okay, thank you. So I'll switch off my mic so you continue your presentation. Thank you.
So just to ask, can you all see my screen in my presentation?
Really, I don't think I can see. Zakwan,
Okay. I'm trying to share my screen again. Share the screen. Can you see it now?
No.
Okay, I don't know what's wrong with the sharing the screen. Okay, let me just try something quickly.
Archit, can you help Maren to share the screen, please?
Maren, can you see at the bottom, there's a share screen option?
Yeah, I've just done that. Select share the screen and you're not sharing. So maybe I would try sharing application to see if that works. Because
Okay.
I just said share the screen.
What
So
you can
let me
try, you can try to refresh the browser once. So it will take you out of the table, out of the presentation, and then you can join back again and see if that helps. Sometimes the browser issue comes in. Which browser you are using?
I'm using Firefox.
Okay, that should be good. Just try for refreshing it once. I think that will solve your problem.
Okay, let me just do that then.
Yeah.
Can you see my screen now?
It hasn't appeared yet.
Okay.
I think Abdullah is getting on.
Hello.
Abdullah, can you just
Yes.
wait for this presentation so we can call your name for the next one probably?
Okay. I'm very sorry. My network. I had network problem.
Yeah, that's okay. That's okay. Network is always an issue.
I have actually clicked share the screen.
And then it will pop up and ask which screen you want to share.
Yeah, so it's just me. You can share the screen, and they say, and then I select share, and that's what I've done.
And then it should appear somewhere.
No idea why it's not.
Able to send your presentation to either Zakwan or Ajit, and then they can share it, and then you can just go through the presentation.
Yeah, I think that's a better suggestion.
It looks like your sharing is not working.
Send the presentation to me, and then on your behalf, I can run the presentation.
Yeah, I'm sending that to the. Can I just send it to
You can
the chat
send.
or
Yes. You can send it
the
through chat.
personal?
Yes, you can send
Yeah,
it to
okay.
chat to the
Let me.
personal message.
Yeah, let me. I'm sending it to you right away.
Okay.
Okay.
Could you locate me, or shall I drop you a message?
Yeah, I've located you. No,
Okay.
Ajit, right?
Yes.
Yeah. I'm just sending that.
Yes, I think I got that one.
Okay.
One minute. Let me share my screen. Wait, coming. 1 second. Let me close a few. I'm sharing my entire screen, and then I'll pop up it. So is it showing now?
Yes, I can. Yeah, I can see your screen.
So I'm going in slideshow mode. I hope it is just popping up the complete one now.
Yes, I see it now.
Okay,
So
just guide me when you want to switch the slides.
All right. Okay, I'm going to start. Good afternoon, everyone. My name is Marin David Dangut. I'll be making a presentation about our paper, which is titled Aircraft Predictive Maintenance Modeling using a Hybrid Balanced Learning Approach. The co-authors to these papers are Dr. Akon Scarf and Ian K. Jennings. Next slide, please. Next slide. So I'll be basically talking about the background of the work, and then I'll speak about the motivation, and then I'll take you through the methodology, emphasizing on the proposed approach, and then I will talk about the key finding, and then I'll make conclusions. Next slide. Can you click again? Next. Next. Okay. Talking about the imbalance learning. With the current technological advancement, especially with the advent of Industry 4.0 or the Industrial Internet of Things, data is becoming more and more available, and this data is coming in with challenge, some imagining challenge. The existing machine learning algorithms actually are limited to handle some of these challenges. The well-developed algorithm are required to deal with this type of problem. The reason why this traditional learners algorithm are not really being able to meet up, because they are built up with some kind of assumption. One of the assumptions is that the data set is balanced, and another assumption is that the cause of misclassification is the same. In reality, there are subdomains that do exist, that the data is not imbalanced. And the example of that is in the aircraft component fault monitoring, whereby the system is expected to function well, which will generate more of healthy data and having a fewer fault. So in that case, the data will be imbalanced. And learning from the imbalanced data set is quite challenging in machine learning. So this imbalanced learning is a domain in machine learning that try to deal with that problem. So most of the time, why is it important to actually predict the class that have a less representation? In most of the case, you can see that the class that has less representation is most of the time the class of interest, as we may see. Next slide, please. So the problem with the class imbalance problem I've said is the issue is if you're training the data with this type of data, the algorithm will become biased toward the majority class. And because of the reason is because the loss function that is used is attempt to only optimize the global quantity such as error rate, not really taking the class distribution into consideration. As a result, the overwhelming class will be well classified, and then the minority class will be misclassified. In some worst cases, if the imbalance is quite extreme, it will consider those points as outliers or noise and drop them. So the learning algorithm will simply generate a trivial classifier that will only learn from one class, that is the class that has majority. And that is why the reason in this type of learning accuracy is because you may have a high kind of accuracy, but while this type of the classifier have actually learned from just one class. Next slide. So can you maybe run it down to get everything? So this is to give a background, because this work is actually on a predictive maintenance. So in predictive maintenance, in aircraft, actually aircraft is expected to function, and that's a cycle of aircraft. So during the aircraft operation, if a fault is detected, when the aircraft lands, that's when the problem will be fixed before it take off. So looking at it in maintenance of aircraft, there's what we call the time-based maintenance, which is like the corrective maintenance or the preventive maintenance. In this type of maintenance, when the fault is detected during the flight, the aircraft land, then the engineers will carry out shooting, and then determine the exact failure, and then the part will now be ordered and then replaced. So we can see that that type of maintenance is prone to delay. And then that takes us to what is called the condition-based maintenance in order to avoid such delay. In condition-based maintenance, there's a diagnostics approach whereby the system in the flight operation, if the fault is detected, it gives exact fault, so that when it lands, then the aircraft would be communicate with the engineer, so that when it lands, the part will be available and be fixed. So in that type of method as well, you can see that we will shorten the delay. But in order to actually further optimize this, so there's what we call the predictive maintenance, which will involve you having to run a predictive model to predict this failure before time, so that when the aircraft, before the aircraft even take off from point A, you have already known that it will fail in the next phase. So parts will be available, engineers will be ready, and when the aircraft land, it will be fixed on time. As we can see, the actual departure time will be the same as scheduled departure, and in that we are cutting the downtime. Yeah. So this is where we're coming into the a predictive model. Next slide, please. So yes, in this, the motivation of this work, we use the data set from the aircraft, which is known as the central maintenance system data set. Is a data set that give the warning messages or failure messages from different subsystems in the aircraft. In this data set, it's a heterogeneous data. It's not just numeric. So, and one thing we target is we target the unplanned breakdowns. You know, maintenance, we have kind of scheduled time that maintenance is carried out. So there are failures that occur that are not planned. So the reason why we focus on this type of failures is because of their importance. You know, the companies are saying, or they are saying that those type of maintenance, though some of them don't often occur, but if they does, the cost is always high. So, so reduction in those type of failure, even to any percentage, will bring a significant benefits to airlines. So that is why we focus on this. And this type of failure in this data set, just rare, there are few of them, and that makes the data highly imbalanced. Next slide. Next. Okay. I wanted to say this is just to show you how this the imbalance is. A normal imbalance is extreme. We can see that the positive level, which is related to the unplanned breakdowns, and there is 0.0% to about 99.99% the failure messages that do not relate to unplanned failures. Next slide. Okay, so having that problem at hand, we decided to look at different solutions to this imbalance problem. Of course, there are different solutions that exist. We try to put them into three from the literature. There is a data level approach, whereby you try to sample this data set, either oversampling it or downsampling. In that case, they have some of their drawbacks. If you are trying to oversample the data, you are adding some new data points, you are altering the structure of the data. And if you're trying to downsample it, you may be taking off some information data points. And then there is the algorithm, by the standard linear algorithm will be modified in some way in order to respond favorably to these classes during learning. And there is the hybrid approach, which involves on one or two to more of this approach to optimize or to gain better performance. So we are actually looking at the hybrid approach. Next slide. Then you can click next. Okay, so yeah, this is we actually the methodological approach. We actually follow the data knowledge discovery process strictly. As you can see, we have sources of data which will represent this failure or warning messages coming from different subsystems, which form the raw data. What we did is we perform the cleaning of data, which will involve taking out some outliers, null values, and all that. And then the next step is we transform using the future engineering techniques. And then after transforming the data set and for the machine learning algorithm, we now apply the machine learning algorithm. This is where the contribution of this work come in, because we propose a method to actually deal with this highly imbalanced problem and looking at this nature of this data set as well. So the method is to deal with the pattern recognition and classification. And after that, we make our evaluation, which will give us a insight for more decision making. Can you go to next slide, please? Okay, so this is the structure of the proposed method that we implement. First of all, you can see the first step is to pre-process the data. We did our future engineering, I've said. So now the transform data, we apply the mixed Gaussian process algorithm with EM. It will cluster this data into different clusters, and then in each cluster, we now apply the bagging and busting method in each of these clusters, and at the end, which is the step 4, we combine this to get the optimal classifier. So the whole our data set, which is the testing data set, we now use it on this classifier, and then we obtain the result. So this is what we implement. Next step, please. Next slide. So yeah, quickly, this is the result we obtain. We actually use the random forest as a base classifier. Why we choose random forest? Because the method is a kind of ensemble method. Because as you can see, we are combining the unsupervised method, which is the clustering, and then the supervised method, which is the classification in each of those clustering. So we use random forest, which is a sample-based method as a base. Compare our method. So we components, as we can see, the components are identified by functional identification numbers like the 4000 KS, the 4000 HA, which represents this component. And then we measure the precision recall and F1 score. From this result, we can see that our method actually have a significant improvement. And then, yeah. Another thing that I would like to say here is that the imbalance ratio, we see that it affects. So the higher the extreme, the imbalance problem, it becomes difficult and the results decrease. For example, in the case of the 5RV1, which is about 0.039 imbalance ratio, we will notice it has a better result than the ones that are maybe the 4000 HE, which is a bleed valve, which is about 0.024. Next, please. Yeah, so to show you the rock off of the pressure bleed valve, if you can see that we obtain about 80% of the true positive rate. Next slide. Yeah, again, this is to show you the confusion matrix. Looking at this electronic engine unit, you can see that out of the 31 failures within the time, we can see that the model is able to predict 622 out of 9, which is about a 70% prediction rate. Yeah, next slide. Okay, yeah, this is to, again, another component. This is a pressure bleed valve. Out of the 9 failure that we can see here, this 7 plus 2, we can see that the model is able to predict 7. It misclassified only 2, which gives us about 80% prediction rate. Okay, next slide. Yeah, okay. In conclusion, I have actually talk about the data set we use in this research, which is unique in its nature. It's not actually most time used for predictive modeling because of this heterogeneous and complex nature. I told you about the challenge of the extreme imbalance data set. Actually propose a method by integrating supervised method for making detection. And after implementation, the method was able to find the important log messages that hold a direct link to the causes of these failures. And again, another thing we discovered that it showed effectiveness in predicting the extreme rear failures. And then again, the proposed method we use, as I've said, precision recall and F1 score to measure. And the result also show robustness in predicting the failure within a defined range, because the predictions, we try to make sure that it's not too is predicting the failure and it's not too close to the failure. So in that, we are able to measure how it was able to make prediction within a defined window. Next slide. Thank you very much. Any question or any contribution?
So any questions from the audience? Okay. In that case, I'll ask one question. So, Maren, when you're training the neural net, like, are you using the messages, or are you using the component failure data to train it, or is that like combination of both?
Actually, in this implementation, we didn't use the neural network. We actually used the mix of Gaussian process, like I've said, which was able to cluster this data. So it's the failure messages. So we actually transformed these failure messages to be able to be used using the feature engineering, as I've said. So we then use what we call the ensemble learning approach at the end, because these clusters we are then classified, and then the results will be combined together using a voting method. So yeah, that's why you can see that we're comparing with random forest approach.
Oh, okay, the random forest. Okay.
So yeah.
So it's a combination of the messages like you're using to.
Yeah, the failure messages, in the data set, these failure messages are coming from different subsystems in the aircraft, like the APU. So the data it spans over like 7 years, and in the data we have about 60 aircraft. So we divide the data into two. We have the one we use it for the training, the model, and then the one for test. So we train the model using those failure messages, and the target event is on planned failures, not just any component that is replaced due to unplanned breakdown is what was our target. That was our target.
Okay. All right. Thank you.
Yes.
So any other questions? Otherwise, I'll move on to the next session. Sakwan, do you want to take over for the next two sessions?
So let's go back to the previous Abdullah. Abdullah?
Hello, yes, can you hear me?
Yes, I hear you very well.
Okay,
Is
great.
your presentation?
Yes,
And
yes.
so our next speaker will be Mr. Abdullah, who is going to talk about emerging challenges of digital aircraft operations and knowledge management system. The floor to you, Abdullah.
Okay. I'm just trying to share my slides.
Abdullah, at the bottom of the screen, you can see the share screen option.
Yeah, yes.
Yes. Right.
Okay, great. Can you see my slides now? Hello.
Slides.
See your slides. Just
Hello.
it's better if you can put it in full screen or slideshow mode.
Oh, yes, yes. Can you see my slides now?
See, you can start.
Hello.
Abdullah.
Can I start now?
We see it and hear you as well.
Okay. Good afternoon, everyone.
Yes, go ahead, please.
Today I would be presenting a paper on the challenges of digital aircraft operations and maintenance from a knowledge management perspective. So before I begin, the co-author for this paper is Dr. Ibshin Fan, and I would like to introduce the concept of knowledge management first, which has to do with the creation, storage, and sharing and transferring of information. But there is two aspects of knowledge management. There's the organizational perspective, which is about strategic competence from the organizational point of view in terms of people and processes. And then there is the information system perspective, which deals with IT systems and expert systems. So that is from the information science perspective. And so this paper would be mainly based on information science perspective, as the research is in the context of aircraft maintenance record keeping. So in the last decade, there has been a lot of proponent of digital record keeping in the aviation industry. As we know, it's a very strict and complex industry in terms of standards. So the IATA, which is one of the big players representing over 80% of airlines in the industry, came up with a guideline on paperless aircraft operations and maintenance. And the initial problem was that the lessors who merely own the aircraft and lease them out to the airlines were not sure about moving on to digital records, as there were some challenges with technology. There wasn't regulatory standards in place, and then the equipment manufacturers were also worried about cybersecurity, and then the entire infrastructure in terms of data systems, interoperability, and so on were major challenge. But so far, progresses have been made. There have been technologies like the RFID, like the e-signature that has really helped in this process. But um, going forward, we found out some certain challenges that actually need to be tackled if digital aircraft operations and maintenance is to be achieved in a more effective and efficient way. The most important point here in this slide is that all aircrafts coming out from 2020 are expected to be paperless and in digital form in terms of records, and all existing aircraft that goes into major or heavy maintenance are going to come out paperless from this year. So this is a significant leap in the industry in terms of digitization, and that is why understanding the problem and challenges that comes with this leap is important. From the context of this research, we found out that um, typically an aircraft will include about 11,000 to 20,000 papers in a year of operation, and this amount to huge records when it comes to transfer of assets or lease returns. And therefore, generally, um, an aircraft could cost 2.5 to 4.5 million in terms of actually auditing those records during the transfer. And this is according to the International Bureau of Aviation. And then generally, um, it consists of about airline aircraft maintenance consists about 9% of the revenue, which is about 69 billion. That is huge. But another important point is that International Bureau of Aviation actually came up with a report on challenges of delivery and redelivery, which points the fact that 60% of the challenges when transferring assets and giving them back, it's on records. Why is it on records? Because it is mainly on paper, and you have to go through months and months and months of records with experts to evaluate and audit them. Now, if by any chance a record is missing from an airline operator or the stakeholder or the lessor or any of the MROs, it means that that component is virtually, or the aircraft itself decreases its value or even not useful at all, because just back-to-back traceability cannot be established and nobody knows what happened between that period. And that's why digital records is important. Now, there's another report that comes out from Cambridge, which actually looks at the information perspective of it, the technology perspective, and four recommendations came out from it. Now, from these recommendations, we found that two that are very, very critical in terms of information record keeping. The first one is the interoperability, which requires semantic software and cognitive systems, which I will discuss in depth throughout this paper. Secondly, is the development of frameworks and standards for data interoperability. So again, we see the idea of Data interoperability, heterogeneous data comes up a lot in the literature, a lot from the industry, talking about this, how this challenge affects the industry. Now, we have outlined four main challenges that we found to be critical in terms of the development of digital aircraft operations and maintenance. The first one is the establishment of common regulatory standards. So now, this has to do with the kind of various standards that exist from different authorities. For example, EASA in Europe, or another one in Asia, or another authority in Asia or in Africa. There's so many different standards, and when you lease your aircraft to different jurisdictions, it means different kind of records and different kind of formats, and that's a huge challenge. Secondly, if you introduce those universal standards, how well is it that the possibility of acceptance, and at what rate each is jurisdiction going to accept? Thirdly, is the adoption. So the adoption also has to do with, for example, challenges of how you keep the records, how well you want to use that technology or not. So, for example, some are already adopting e-signature, some are reluctant to adopt it. Finally, is the harmonizing of technological solutions. Now, this is the main area that we think is very important, as the first three are more of managerial and like trying to enforce them to make the people and stakeholders to use it. But the harmonizing of technological solutions is the area that is very critical, whereby all the technologies that we have and all the progress that has been made so far can be extended to be more efficient. For example, in the context of data interoperability, or maybe framework for developing the MRO IT systems, or trying to make them to understand each other and be able to integrate data from different systems. So when we look at what has been done in the industry, we found out that there are three major categories in which knowledge management is considered from information perspective in the industry, and there's some relevant research that has been done, which is great. So firstly, there is the maintenance and support, which look at maintenance record. And secondly, there is the operations, which looks at including the air traffic management and also unmanned air traffic management. And thirdly is the aircraft engineering and informatics, where they look at how to store knowledge of engineers and so on. And so on the right side, we can see I've outlined about five major studies that we found. Then look at the first one is the aviation safety management, where they look at inaccurate record keeping and insufficient integration of safety data. So what they did was that they developed an ontology, and then tried to develop an ontology-based information system from that in order to improve integration of data. They did presented how they develop it and evaluate it. So it gives an idea on the kind of work that can be achieved. Secondly, is the operation-based knowledge management in the area of aircraft engineering. But this really looked into the organizational perspective, where the knowledge of expert engineers is transferred to the new engineers. So that's more from IT, from organizational perspective. Thirdly is the avionics. In terms of avionics, the kind of work that has been done is trying to conceptualize the knowledge of avionics domain, and then try to understand how and why failures occur, and then what are their consequences. So they develop an ontology based on reuse and alignment, which means they use existing ontologies in that field, and then try to associate cause and effect of that of the failure in that area. And then there is another work on harmonized MRO work task definition, which I will discuss in depth in the next slide. And then also in the area of traffic management, which is somehow similar to the first. So in terms of harmonizing MRO work task definition, what this research did was actually looking at how I think it was Monarch Engineering, which is actually down now as an organization in the UK. But what they did was look at how this company actually analyzes customer bidding and then develop an ontology based on that, based on their existing system that they had, which was based on an Excel and a mini database that they had. And then when they develop this ontology, then they use the customer bidding when it comes in, try to map it with the existing database, map the ontology from the existing database, and then try to compare and find out what task that has been done previously actually match the current bidding. So what this does is actually save time for them to go manually through all the previous work that they have done in order to compare the task and actually give out accurate bidding and that could be accepted by the client. So they use fuzzy match, they combine that together with their ontology, and then they develop a mapping tool that was able to predict or get an output from their records, the maintenance planning document and the tax number and so on to get customer bidding efficiently and more accurately. Now, in the context of maintenance record keeping, the idea here is that there are three components. Firstly, there is the aircraft maintenance manual, which the equipment manufacturers detail how the work can be done. And in that maintenance manual, there is also task card, which references to each part of an aircraft and what task should be done, and also details who does it and the materials or consumables that are involved. So what we are seeing here is that there's actual need of higher level of knowledge representation if you were going to develop a system that doesn't really only look at data structure to do it, but also look at the relationship and semantics of that information in order to understand the knowledge between or the information that comes from similar systems within the industry. So if you use two different systems over a long period, you could integrate that details. So here is one of the records that we are actually reviewing from the aircraft technical report that was given to the university. So in this case, we were using the records of the 737 available at the university. And on the right side is one of the technical records. And on the left is the task card from the aircraft maintenance manual. Now we can see that on the left side, there is defect and there is the action taken. And the blue arrow is showing that the engineer who actually carried out this task was referencing back to a maintenance manual that he applied in terms of taking action for that specific defect. And that is maintenance manual chapter 32, section 45. And that is where I show it here. So what we are seeing here is if you have an ontology, it can reference back to that maintenance task, and it can even know what actually was done, what consumables were involved, and so on. And you can infer a lot of information and find gaps between maintenance record. And so when all this is recorded in automatically and with a system that has good relevant information structure and conceptualization, you could understand and build a lot of reasoning on that. So, and that is why we presented the idea of having an ontology model that consists of four main categories. And these are the most essential or critical aspects of aircraft maintenance keeping that we have found. The first is the aircraft structure, which includes the ATA chapters of the aircraft. So, for example, the fuselage, the APU, the engine, and so on. And then there are the maintenance tasks, which actually details what job needs to be done, who does it, and the consumables. And then there's maintenance personnel, like the technical report that we have seen. So they would be responsible to enter those records. And there's the administrative processes, which are the maintenance processes. So on the right, you can see how we actually related a maintenance task for the fuselage, which is part of the aircraft structure, and the task is the flight crew compartment inspection, and then we detailed how, for example, the ontology is going to have object properties, data properties that actually describe this information. And when information comes from external system or heterogeneously, you could still make sense of it and infer facts from it. So the impact of having a universal model in terms
sorry, Abdullah, just 1 minute left, yeah? Because we are running out of the time.
Yes. I think I'll be concluding after this one. So the impact for the industry would be that if you have an ontology model that is being used to develop systems, if a lessor gives out an aircraft to an airline, and then that airline uses one or two MROs and gives out to another airline which uses more MROs, the digital record can actually be inharmonious, even if it is on digital systems. But what an ontology would do is that it would try to get that record and use the semantics and conceptualization of that domain that you have made and that information structure. And that's why in the green ellipse here, you see the main impact of or an ontology model would do for the industry is to be able to integrate and reconcile that huge amount of record over several span of years. And it's going to make it efficient to for the people and reduction of costs, and also make the process more automated. Finally, the current view in the industry is that the digitization is focused on automating tasks rather than the knowledge management idea that says, oh, we could actually use this data to apply reasoning on this, to apply reasoning in order to make better understanding of this information and for more data integration. And also an ontology comes with terminologies, comes with dictionary that also is very useful in terms of knowledge reuse and sharing. However, in the current perspective, knowledge sharing and reuse is not considered, and also data integration is currently not considered, so it has to be done manually. Finally, so this is the final slide. We see that the digital IT systems that we have today are not a means, not an end towards achieving digitalization, and therefore there is a need for a more robust alternative in terms of digitizing information from those systems. And here are some of the further challenges that we see going forward. Thank you very much, and I look forward to any contribution or question, please.
Any question from the audience? Okay, so let me ask you a question, Abdullah. So you have proposed a universal framework, which looks very ambitious, actually. As
Yes.
you are doing your research, are you going to focus on a specific use case? Because you can convert all, guidance catalog and manual into your ontology.
Yes, this is very, very important. And the idea of the aircraft maintenance manual itself is so huge and cannot be covered in 3 years, to be honest. So what we are considering at the moment is that the 737 at the Cranfield University has a parking maintenance program, and we are going to use that as a case study in terms of all the maintenance tasks that are being done and the parking maintenance program, and that is what we are building a use case on. But fundamentally, we are trying to cover the building blocks that will allow extending the ontology into other aspects easily, which means, for example, ontology alignment and reuse, because the whole idea is to expand it to the industry. So if we're going to build the main building block and then have a use case to concentrate on, it will really help the industry in terms of building further on that.
Okay, thank you very much, Abdullah, and all the best in your research.
Thank you very much.
Okay, thank you. So now let's move to our next speaker, who's going to talk about power drive electronic reliability in more electric aircraft. I think is Dr. Suhaib. Suhaib? Suhaib, are you online now?
Sohaib on the speakers list, but I'm not sure whether he's there on the table or not. Sohaib, are you online? Yes, he's there.
Hi, good. How are you, Dr. Zakwan? Can you see my video and screen as well?
Yeah, we can see two screens actually, Suhaib.
Okay, so let me share my if I can, yeah, let's see. Is my presentation visible to all of you?
Not yet.
Is it now? Dr. Zakwan, can you hear me?
Yeah, no, we can't see your presentation, Suhaib.
Okay, I mean, it's already shared. I don't know what's the problem.
The share screen option.
Yes, I have actually used that. It's
Okay.
already been shared.
Okay, so are you sharing only the PowerPoint presentation option or you're sharing your entire screen?
Actually, it's all screen. So
Can you just then put the PowerPoint on? Maybe that can solve the issue.
now can you see?
Nothing yet. Probably a little bit slow internet, so it will come up later maybe. No, we can't see anything yet.
It's a bit strange. I don't know what's happening.
You just need to send it to him. If you're using MacBook, I think there are some settings you need to do because I experienced that as well. So
Yeah, I
maybe
think you can share it, send it to me, then I can just play it on your behalf.
Yeah.
Okay, so
So just go under chat options. You can see my name. My name is Arijit.
right.
And in the left hand side, you will find the clip button for attach files. You can attach that and send it to me.
So right. So I go in chat.
Yes, in participant, you can find my name directly under the host name.
Right. So
And then you can message me.
okay. Did you get it, Jeet?
I just got something, yes. Hold on a minute. Yes, I got your presentation.
Okay, so
Let me share it. 1 minute. Share screen. Can you see it now?
yeah, I can see it.
So I just maximized the screen in slideshow mode. Just let me know when I have to change the slides.
Okay, that's perfect.
You can go ahead.
So is it on the? It's not still on the presentation mode. It's
I made it on presentation mode, full screen at my end.
Okay.
So can anyone else confirm whether it is in full screen mode or is still showing in editing mode?
Is editing mode, yeah.
It's in editing mode yet, still.
Yeah.
Okay. Hang on. Let me unshare and then reshare thing. Now?
Okay, that's fine now.
Okay, cool.
So I can start now. So good evening, everyone. To begin with, our reliable power electronics group comprising Dr. Suresh, Dr. Andrew, and myself, my VHM Center, and Dr. Ali Raza from A-Star Singapore, would like to thank Test Conference team for affording us this opportunity to present our paper on power drive electronics reliability in more electric aircraft. Next slide, please. For the next 15 minutes, I shall be walking you through this scheme of presentation. Next, please. Starting with what does power drive electronics signify and why their reliability has become increasingly crucial, and what set the tone for this work. Uh, I'll give you an overview of the proposed integrated reliability paradigm for power drive electronics, and then talk about the application of IRP on the electromechanical actuator of more electric aircraft, uh, landing gear system, then talk about results and analysis, and then wrap up this presentation with key takeaways. Next slide, please. So what is power drive electronics? Precisely in the context of this research work, it is essentially a power electronics paraphernalia employed in more electric aircraft to drive the onboard loads and enable actuation functions of the aircraft. So primarily, power drive electronics consists of discrete electrolytic capacitors, diodes, and the main workhorses. Next, please, can you please keep clipping here? That's fine. Main workhorses, that is the power semiconductor devices such as IGBTs, MOSFETs, and HEMTs, the high electron mobility transistors that perform electric power control, switching, and when configured into circuits of or network of various power devices, they enable critical power rectification, inversion, and conversion functions to drive various aircraft loads, and hence assist the associated systems achieve their defined operation at varying frequencies. Next slide, please. So looking at the power spread within Airbus A380 and Boeing 787, we find a mesh of power net that requires optimal control, switching, and conversion of power starting from generation through AC and DC sourcing, and then driving certain loads from, say, lows of 5 to highs of 175 kilowatts. Next slide, please. And this all is made possible by an optimized implementation of power drive electronics, such as MOSFETs and IGBTs in discrete and modular configurations with different voltage, current, and frequency ratings to serve various power topologies within aircraft power network. Two double plates, please. This includes inverters, DC converters, AC-DC converters or rectifiers, etc. So this shows how significant is the power drive electronics requirement to achieve and optimize gradually increasing electrification of the aircraft. The question is, next slide, please. Should we focus on improving power drive electronics reliability for more electric aircraft architecture? And the answer is big yes. And this is because, as mentioned earlier, the trend and drive towards environment-friendly and fuel-efficient aircraft is being made possible by more electrification, which is quite promising, as can be seen in all-electric architecture. So, for instance, starting from 1950s with traditional first commercial jet airliner and moving towards more electric, full hybrid, and all-electric aircraft architectures, the relevance and importance of implementing and integrating highly reliable power drive electronics is growing exponentially. So we need smart reliability paradigms that support this growing trend, and this calls for not only maintaining their reliability but also enhancing it. Few clicks the next slide, please. Thank you. So besides this natural evolution, the context of this paper actually lies in three triggering factors that led to this research work. Firstly, the recent data-driven reliability assessment of Boeing 787 carried out by Michael Pett and his team revealed some critical problems relating to the design, testing, and reliability evaluation regime, followed by the system designers, integrators, and associated vendors. So there were inaccurate design assumptions that brought about performance and functional limitations in components and systems. There were compromises made on certain industry standards to move or push things faster, and that affected the reliability of power electronic circuits relied on several key power control and switching panels. And more importantly, the system design test designs were inadequate. That includes both the limited test coverage and unreliable test methods. For instance, FPGAs were not optimized to identify system failure modes. So such infirmities incapacitate the system reliability and then compromise overall flight safety. The next slide, please, and clicks. So, secondly, the uncertainty over reliability of new materials and packaging technologies is a matter of utmost concern. It is such that the wide band gap semiconductor materials such as silicon carbide and gallium nitride offer physical properties which are pretty superior to those of silicon presently employed for power device applications, enabling devices based on these materials to withstand high voltages and temperatures, as well as permitting high frequency response, greater current density, and fast switching. So these emerging power devices have great potential. However, the technologies necessary to create and refine them are less mature than the silicon technology. So this creates some big challenges associated with designing and characterizing these devices, as well as process monitoring, and importantly, the reliability issues themselves. So the bottom line is, before these devices can gain a reliability of power drive electronics, especially with regard to wide bandgap devices, need to be proven in a composite manner for higher reliability. Next slide, please. And lastly, the inadequate reliability evaluation, meaning that the conventional approaches employ constant failure rate models without considering the loading conditions and their impact on different components and systems of the system. And as a result, there is no overall system reliability quantification. So in addition, the conventional approaches have a flat structure, meaning they cannot assess the reliability impact of different components or subsystems on the overall system and then identify the vulnerable part. So they do not provide any guideline for reliability enhancement, meaning there is no substantial information that can be fed back to the designer to augment the design for reliability. So, what could be the more effective method of determining the power drive electronics reliability for more hybrid and all electric architectures of aircraft? Next slide, please. The answer lies in an integrated reliability paradigm. It is a systematic framework for modeling and evaluating the reliability of power drive electronics from device to system level. So it comprises three reliability levels, RL1, RL2, and RL3, adopting a typical bottom to top approach. And at reliability level 1, the reliability modeling of individual power devices is undertaken to ascertain their failure rates under varying operating conditions. The array of power devices which we term as power devices network forms a subsystem of reliability level 2. At this level, the composite reliability modeling of the drive network is carried out, taking into account the failure rate of devices at RL1. Finally, at reliability level 3, the overall system reliability is evaluated by formulating an integrated system graph uh, uh, for the power system architecture and the reliability of the system in the test. In a nutshell, the proposed integrated reliability paradigm provides an effective approach whereby the impact of systems operating in loading conditions such as thermal stresses, voltage levels, power, loss, vibration, etc., is considered as a whole in the calculation of the failure rates at the device, subsystem, and the system levels. So at different levels, failure characteristics, power devices, and subsystems are investigated, and static reliability evaluation is then undertaken. Next. So in order to check the viability of proposed integrated reliability paradigm, we carried out the reliability assessment of the electromechanical actuator, approximate the landing gear using the Simulink and optimization toolbox and reliance software. As can be seen, the EMA would convert the electrical power supplied by the power network of the aircraft via power drive electronics into mechanical power, and then the mechanical power is transferred to the gear by a nut screw MPT, which is a mechanical power transformation. So primarily, the actuator control unit interprets the final command to drive the EMA, and it does so through the motor controller system, which generates the pulse width modulation signal for the power devices network. In this case, forming the power inverters to eventually move the EMA at required torque. So as we apply the IRP process at the RL1, the failure rates of the power electronic devices, including IGBTs, diodes, and capacitors, are determined using the parametric values of voltage, current, and power, as well as the temperature obtained during very low conditions of EMA while landing, taxiing, and takeoff phases of the aircraft. We also factored in the dynamic disturbances that present mechanical shocks to PDE and cycle them over a period of 100 hours. So, at accordingly, we employed the minimal cut set scheme. So we defined the minimal cut set for the load points. In this case, the EMA on the left wheel and then EMA on the right wheel of the EMA system. And then based on the reliability level 1 and 2, and then integrated system grounds, the integrated reliability evaluation was carried out by employing the IRB process. Next slide, please. So coming to some results, as you can see, the sensitivity analysis of failure rate of IGBTs and its impact on the reliability of electromechanical actuator is shown here. As is evident from this graph, the higher the failure rate of IGBT, the lower the system reliability. And this is in correlation with the thermal cycling the IGBTs were exposed to, thereby implying that higher thermal temperature tends to increase the degradation in IGBT reliability and subsequent performance, which may result in the overall EMA performance degradation and reduced reliability. Next slide, please. So here, comparing the cumulative reliability with respect to EMA approximate left wheel and EMA approximate right wheel of landing gear, we can see that they both maintain high reliability equal to or greater than 0.991 in this case, even after 10,000 flight hours. And this includes the taxiing, takeoff, cruising, and landing phases, with stresses more prominent during the landing and takeoff phases. This implies that the differences in reliability of power drive electronics which serve the EMAs are not significant, as evident from this, and resultantly both can be implemented in any architecture considering their high reliability. So this forms the crux of proposing this framework that can be uh, exploited to determine safe implementation in ME architecture. Next slide, please.
So
So
Suhaib,
with
1
this,
minute
I
left.
come to the end of my presentation with certain key takeaways. First and foremost, the optimal MEA operation places an increased demand, assuming on assuring availability of highly reliable power semiconductors devices. To be more precise, the power drive electronics in this case. And this can be made possible with integrated reliability development that enables an optimized reliability assessment from device to the system level. And then the factoring in of highly representative system mission operating conditions is key to exploiting IRP for optimal thermal and power management so as to enhance the reliability of power devices and various topologies they build. And last but most importantly, it provides a framework that facilitates environmental optimization, designing and implementing redundancy, and improving preventative maintenance strategies related to MEA or all electric power systems in future. So with this, I come to the end of my presentation. If you have any questions, go ahead.
For your any question, guys.
What was the question? Sorry.
I'm just asking, is there any question from
Oh, sorry.
okay, so there is no question. Thank you very much, Suhaib, and all the best. Yeah.
Thank you very much, Ozarko. Thank you.
So let's move to the last presentation in our session today. Is about a probabilistic remaining useful life based on DCNN. And our speaker is Mr. Jian Jiao. Jian Jiao, are you here? Okay, may I ask you to turn on your mic and camera and share your screen, please? I think you're ready.
I think you are still sharing your screen. Can you put it off, please? I am putting you as a speaker. Can you access your mic and camera now, Jing Yu? Yes, you can. Sohaib, can you please put your mic and camera off, please? I think you're still sharing your screen or something.
Can you see my presentation?
Yes.
Please go ahead whenever you are ready. Can you hear me?
Yes, yes.
Could you please start?
Okay. Hello, everyone. It's a great honor for me to have this opportunity to share our research work here. My name is Jin Yao from Xi'an Jiaotong University. My presentation is about probabilistic remaining useful life prediction based on deep convolutional neural network. The whole presentation contains the following four parts. Modern big data techniques has led to the popularity of prognostic and health management, both in the research community and within industry. One important ingredient of PHM is remaining useful life prediction. That is the estimate of how long a system or machine may continue to operate unhindered. Given the complexity of modern industrial systems and the quantity of associated monitoring data, data-driven model-based methods based on machine learning have shown successful results. In RUL prediction, traditional machine learning algorithms need handcrafted features as their inputs, which limits the performance improvement in the big data era. Thus, deep learning, which allows automatic feature extraction without extra domain knowledge, has become one of the most promising data-driven model-based approaches. However, most of these deep learning models only provide a point estimation of the RUL, which means that the prediction uncertainty is often ignored. The quantification of the prediction uncertainty is important for assisting decision-making, including identifying alternatives in PHM systems. Without prediction uncertainty, it would be impossible for decision makers to quantify the trustworthiness of deep learning model results. The uncertainty mainly contains two parts: epistemic uncertainty and the electoric uncertainty. Epistemic uncertainty is the model uncertainty introduced by the representation capability of models, and many scholars introduced the Bayesian deep learning framework to model this uncertainty. Another uncertainty is electoric uncertainty, caused by factors such as input uncertainty imported by error of measurements or operating condition. Keynes assumed Gaussian noise in degradation process to model the uncertainty, but not feasible. Liu and Jensen used the bootstrap method, but this method is time-consuming. Thus, in this work, We aim to simplify the process of electoric uncertainty quantification and provide a probabilistic IUL prediction framework with flexibility to work with existing deep learning models. The next part is the methodology. We first review point estimation method and then introduce the probabilistic IUL. Mathematically, the real RUL YT at the time stamp t can be expressed as the true RUL plus the additional noise, where the mapping function f denotes a representation function with an input data xt and a alert parameters theta. Given the training samples, the parameters theta can be estimated by minimizing the mean square error loss function when the noise follows the same Gaussian distribution at all time steps. Then the point estimate of yt at the time step t is calculated while the obtained optimal parameters. However, the above point estimation of the RUL have the following two problems. One, it cannot provide a confidence interval of the target prediction caused by electoric uncertainty. It only assumes the noise follows the Gaussian distribution, but in the real scenario, the interference is not always Gaussian noise. Probabilistic RUL prediction at time t can be expressed as modeling the conditional distribution of RUL. The input data can also represent multiple historical observations with a sliding window. We established probabilistic RUL prediction framework using the parametric and non-parametric methods. For parametric approach, given a specific distribution, the MLE-induced loss is used as a loss function to optimize the corresponding parameters of the representation function. In this work, we assume the conditional distribution follows a Gaussian distribution. Then we apply the negative log likelihood of all training samples to construct the corresponding loss function. Furthermore, a large sigma I is undiscernible, especially when the RUL is short. We add a variance indicator in the final loss function and modify the loss function. The main disadvantage of the parametric approach is that it's distribution specific. If the assumed distribution cannot represent the real-life uncertainty distribution, the performance will be suboptimal. When it is difficult to determine a specific distribution, a non-parametric approach is possible. For the non-parametric approach, multiple predict RUL at a quantile level Q can be obtained by minimizing the quantile regression loss. With that, given multiple quantile levels, the final optimization problem using the quantile loss of all training samples can be represented as their summation. Although quantile regression is distribution-free, it cannot obtain the whole distribution. In the above probabilistic RUL prediction framework, one important detail is left unanswered. That is how to construct a deep neural network incorporating historical operations and RUL. Among different deep neural networks, DCN possessing a strong ability of representative learning has become increasingly popular and achieved significant success. Meanwhile, the ResNet proposed by Kai-Ming He is one of the most popular backbones in DCN, and its deep version is the first DCN extending the human baseline accuracy. Thus, in this work, we construct a M-ResNet NAT, which is shortened and modified version of ResNet, benefiting from the flexibility of the neural network. The number of final outputs can adapt to the target parameters of the parametric and non-parametric method. The next part is the experimental verification. The CMAPS dataset is a turbine-fan engine degradation simulation dataset generated by CMAPS, a suitable platform that can record measurements from different sensors corresponding to predefined health-related parameters. This dataset consists of 4 different subdatasets simulated under different compositions of working conditions and 2 fault modes. A total of 21 sensor measurements are collected in each subdataset. That includes a fleet of engines. In this work, we choose FD001 and FD003 with the same condition and different fault modes to verify the performance of our constructed probabilistic RUL prediction framework. The flowchart prognostic modeling and the RUL prediction is illustrated in this slide. The first part is the sensor selection. There are some measurements whose variance are too small to provide any useful information. Thus, we drop any measurement whose variance was smaller than a constant threshold. The second part is normalization. For the stability of model training and testing, each sensor measurement is normalized using 0 to 1 normalization. The third part is simple generation. In this work, we set the window length equal to 30. Thus, the dimension of each training sample was 1 times 30 times 40, which represents an input channel window length and the sensor number respectively. The final part is the RUL prediction. The training data set is used to train the neural network, and the trained network is further used to predict the point estimation and the confidence interval of the RUL. From the experimental results, we can observe that the probabilistic RUL prediction framework can achieve considerable results and even higher accuracies than the point estimation. Performance of the parametric distribution estimate is similar to the non-parametric method. This may be because that the true prediction uncertainty obeys a Gaussian distribution to a certain extent. To further verify the performance of our probabilistic RUL prediction framework, we also compare our approach with other state-of-the-art methods. We can observe that our proposed approach can achieve a slightly better performance than other methods in both datasets. In addition, to make the electrolytic uncertainty quantification more understandable, we show the 90% confidence interval of the predicted results. From the visualization, we can draw the following two conclusions. One, two methods both provided a decreasing uncertainty over the circle, which is very useful for the IUL prediction in practice, as the shorter IUL is associated with higher risk. When, when the trade-off parameter lambda of the parametric approach is too large, the learning procedure will pay more attention to the variance indicator, which means that the model would prefer to output a relatively small variance. From the perspective of probability, a large lambda means we assume a strong pair of variance in the loss function, which might distort the assumed parametric distribution. It comes to the conclusion. When we construct a probabilistic IUL prediction framework using parametric and non-parametric approaches to estimate the probability density of the target outputs based on a DCNN model. Our proposed framework can provide not only a point estimate of the IUL, but also the associated confidence interval of the IUL prediction. 3. One public available dataset was used to verify the performance of our solution, via comparison with other state-of-the-art methods. Thanks for all your listening. The source code will be released at the GitHub page.
For your nice presentation. Any question, James? Any question from the audience? Okay, so let me ask you one small question, please. So you talk about your method. You are choosing. You have a sliding window, which is F. Does this window size has an impact on the accuracy of your RUL prediction?
Sorry, I can't hear.
Okay. Have you done any sensitivity analysis regarding the impact of this window size on the accuracy of RUL prediction?
In this paper, we didn't make such experiments.
Okay. Do you think the size window will have an impact on the accuracy of the prediction?
Yes, it will make some influence on the final results. So in practice, we usually choose 1,000 length or 2,000 length.
Okay, that's fine. Thank you very much. So by the end of this presentation is coming to the end of our session today. I wish you, the best. I hope to see all of you at the last meeting, which is coming to start in 35 minutes, isn't it?
Yes, I think we are going to shortly start the last session, which will be at 14:45, the award presentation, and then there will be the call for next year's conference and closing remarks. And all these things will be happening in the main auditorium. So we are closing this session shortly, and I request everyone to go to the next one, the live auditorium one, where the workshop is going on. they can join there, and soon they will be taken there for the last closing sessions and other things. Thank you.